All right, so I think you're going to like this video. In this particular video, we take advantage of the value of K and our understanding of the position of an equilibrium based on that value of K to make an assumption. And that assumption greatly simplifies what would otherwise be a diabolically hard problem to solve, certainly in some instances. So like I said, I think you might like this. We'll make life a little easier in some instances. So as you can see, a lot of equilibrium constants are very large or very small. In fact, when we go a bit further, when we get into acids and bases and solubility products, most of the equilibrium constants are very small. And so when Kc is small, the equilibrium calculation is often simplified by making an assumption about that value of Kc, or based on that value of Kc. And that assumption, as I said, uses the fact that it's so small. So let's look at a couple examples, large or small. So here's Kc equals 4,500. So in terms of position, the equilibrium lies far to the right. Right? Very large equilibrium, so concentration of products greatly exceeds the concentration of reactants. Okay, so that's one particular scenario. What if the value of Kc is 2.2 times 10 to the minus 8? So that's a really small value. So here, equilibrium lies to the left, far to the left. And the concentration of reactants is much greater than products. So those two scenarios just illustrate where the equilibrium lies, and it does indicate to you something about concentration of reactants relative to products. And so we use that. So for example, if we think about this very small value, if it lies far to the left and it's mostly reactants, concentration of reactants is going to be quite high. The change is going to be pretty low. The change to get to equilibrium because of the value of K is going to be low. So that C, or change in our ice table, is going to be very small. Oops. And we use that fact to make our assumption. And so why don't we find out how that's going to work? All right, so here we have a reaction. Decomposition of water at 1,000 degrees Celsius has this very small value of K, 7.3 times 10 to the negative 7. That's a really small value. So let's go ahead and make our ice table. So initial concentration of water, 0.25 moles per liter. Initial concentration of oxygen and hydrogen are 0. So this is going to change by a value of 2x, or negative 2x, based on stoichiometry. Oxygen will change by a value of positive x, hydrogen by a value of positive 2x. So now we have our equilibrium concentrations, 0.250 minus 2x, x, and 2x. So we can go ahead and make an equilibrium expression. Concentration of oxygen multiplied by the concentration of hydrogen squared divided by concentration of water squared, and we can plug in our numbers. 7.3 times 10 to the minus 7 equals x multiplied by 2x squared all over 0.250 minus 2x squared. Okay, and so at this stage I would look for a perfect square, and I would see that I can't get one. X multiplied by 2x all squared isn't going to work, and that's a perfect square, but this is the problem here in the numerator, and that in fact simplifies to 4x cubed, And so what you end up, if you were to solve all of this, you'd end up with a cubic equation. And there is no easy way to solve a cubic equation. That's a real can of worms trying to solve that one. But what I have is this. This is what's important. This 0.25 minus 2x. And so this is where I can make my assumption. Okay, so again, if we look at the value of k and we consider this, what we're saying here is the equilibrium is going to lie far to the left because of the value of k, favoring reactants. So that's a relatively speaking, a high concentration, 0.250 moles per liter. And it's going to change, but that change is going to be really, really small. And so in terms of sig figs, in terms of percent difference, that minus 2x term is going to be pretty inconsequential. And so that forms the basis for our assumption. And so we're going to carry on and make our assumption. And so if you're changing the problem in this way, you must make the assumption. And the assumption basically goes like this. Oops. Because Kc is so small, assume that the concentration of water, 0.250 at equilibrium, is approximately equal to 0.250. So what we've said is that negative 2x value, that component, that change component, is going to be inconsequential, and it's not going to actually change the concentration. And so instead of having this 0.250 minus 2x term at equilibrium, we just have 0.250. And you'll see that greatly simplifies things. So here we go. There's our equilibrium concentrations, but we've now said this is actually going to be 0.250 because of the assumption, and so we just carry on with our calculation. I'm not going to rewrite the entire, well, yeah, we'll rewrite the entire equilibrium. Oxygen times hydrogen squared over water squared, and our equilibrium value is 7.3 times 10 to the minus 7 times x, equals, not times, equals x times 2x squared all over 0.25 squared. And I can solve that just by getting rid of that minus 2x term. I still end up with a cubic term, but I don't have a cubic equation. And so when I solve for x here, when I isolate x, I get, just to show you the entire calculation, 4.56 times 10 to the negative 8 equals 4x cubed. 1.14 times 10 to the negative 8 equals x cubed. So the cube root of that can be obtained through your calculator. That's not a very hard calculation. You should be able to handle that. And that actually equals 0.00225. And so there's our value of x, 0.0025. And so our equilibrium concentrations become, concentration of oxygen was x, which is 0.00225 moles per liter, 3 sig figs. Concentration of hydrogen is 2x, so that's 0.00450 molar, and the concentration of water was 0.25 minus 2x, which was 0.00450, which equals 0.246 molar. And so we can sort of think about, was our assumption valid? And this is the This is the one we're interested in. And it's changed, but that's a really small change. If you think about its change, that's changed in the thousandth place, 1/1000th place of our concentration. And so we can do a quick little check, basically the 5% rule in science. So we can quickly calculate the percent difference. And so the percent difference is calculated as follows: 0.250 minus 0.246 divided by 0.250 times 100. And what do we get? We get 1.6% difference. And so in science we talk about a 5% difference being well within the boundaries of experimental error. And so in this case that assumption is valid because the difference in our concentration that we would expect, we'd expect a no change in concentration, 0.250. Well, it's actually 0.246, but that's such a small difference that it's certainly within the realm of experimental error. And so that makes the assumption valid. And so that assumption, as I mentioned, really simplifies the problem. It saves you having to solve a cubic equation, and when you make that assumption in other situations, it'll save you having to use a quadratic equation. So how do you decide when to make the assumption? Well, there's a 100 rule, and so we follow the 100 rule. So the 100 rule basically says that the initial concentration divided by K is greater than 100. You can go ahead and make the assumption. So in this particular example, initial concentration divided by K. If that number is greater than 100, we can make the assumption that number is in fact 342,000 something. 342,465, which is much greater than 100. So that means make the assumption. So that's what you need to look for. You need to look for that 100 rule with your initial concentration and your value of K. And if you can make the assumption, you go ahead and make it. So you have to quickly assess the value of K relative to the initial concentration. So value of K relative to initial concentration, if it's greater than 100, when you divide K into the initial concentration, then you can make the assumption. So in this example, we have to end up rejecting the assumption. So let's just go through this. So hydrogen fluoride is synthesized by combining hydrogen gas and fluorine gas. And so we do have concentration, so let's get our equation first. H2 plus F2 yields 2HF. So there's our equation. We have concentration, so we're going to create our ice table. 1.0, 2.0, and 0 for hydrogen fluoride. Why is it 1? 3 moles in 3 liters. 1 mole per liter. 6 moles in 3 liters. 2 moles per liter. Change. Minus x plus 2x. At equilibrium, 1.0 minus x, 2.0 minus x, and 2x. Now, Kc equals HF squared over H2 divided by F2. There's your equilibrium expression. And you have to see if you can make the assumption. So here's our value of K, 0.0115, and here's our initial concentration. Well, which one should we pick? Pick the lower one, because if it works for the lower one, it's going to work for the higher one, obviously. So, initial concentration, 1.0, divided by K, 0.0115, equals, and that is equal to 86. So, not greater than 100. So you cannot make the assumption. And so you'd have to go ahead and solve an equilibrium problem using the quadratic equation. You're going to substitute these values, 1.0 minus x and 2.0 minus x, into your equilibrium expression. That's going to yield a quadratic, and etc., etc., etc. So if you want to see the solution to this problem, you can keep watching after the video concludes, and I have the solution there. It might be worth your while just to go through that process. Again, it's more practice, but hopefully you see in this video I've tried to show how making an assumption can simplify a problem. And when you make that assumption, you have to check, or before you make that assumption, you have to check that you actually can, that the initial concentration and the equilibrium constant obey the 100 rule. That is, concentration divided by Kc is greater than 100. And if it does, go ahead and make the assumption, simplify the problem, take the easy route. If it doesn't, you have to go the long, arduous path. So that concludes this video, unless you're going to look at the answer to this question. Okay, so here's the answer to that problem I was talking about. So if you plug in, remember we can't make the assumption, so we're going to substitute in to our equilibrium expression. So there's our value of k, 0.115, 2x squared, 1 minus x multiplied by 2 minus x. So you get a quadratic equation. So there's our quadratic equation, 3.99x squared plus 0.0345x minus 0.023 equals 0. And so we have to use the quadratic formula. So there's the quadratic formula. Remember, you don't have to memorize that, but you do have to be able to solve it. So we just go through and solve. So it gets a little squirrely, but we get two values of x, 0.0717 or negative 0.804. Two values of x. Well, again, we have to dismiss one, but it's easy. Can't have a negative concentration, and you would get a negative concentration for the concentration of HF. 2 times the negative number, negative concentration, so we can't have that. So we have x equals 0.0717, and that gives us our concentrations. 2x, so 0.14 moles per liter for hydrogen fluoride, 0.9 moles per liter for hydrogen, 1.9 moles per liter for fluorine. So that seems okay, and we can do a quick check. We calculate Q based on those concentrations. So when we put in our equilibrium concentrations we just found, we get this value of Q, 0.0111. Not exactly the same as K, but it's actually only 3.5% different from the given value of K. So again, it's within the 5% difference, which means our assumption was valid. And that actually concludes this video.